Welcome to EDU World Space.
All right, chapter 4, problem number 23. We got two blocks, and side by side, we're pushing with 100 newtons on the bigger block on the left-hand side. And they want to know what is the force that the smaller block pushes on the bigger block with. And the key here is going to be drawing correct free body diagrams. So let's start with the 20 kilogram block. That dot represents the 20 kilogram block. The forces acting on it are mg going down and the normal force going back up. That block's not accelerating vertically, so those are equal. We're pushing on that block with 100 newtons of force to the right. The 5 kilogram block is pushing back to the left, and let's call that the force from block, I can't remember what they named these guys. I believe this is A and this is B. So let's call the force on A from B, right? Now, the key to understanding this problem is a free body diagram also for what's going on with the 5 kilogram block, okay? Because I know there's a Newton's third law pair here. So yeah, we've got the weight going down here. We have a normal force going up here. And then we're going to have the force from B on A. Let me draw that a little bit better because I know that this is an action-reaction pair. So the force of B on A. So let's see here. Those forces are equal and opposite. So force AB is equal to force BA. And if we're going to find one of them, we can find either one because the magnitude of the force is going to be the same. So looking at Newton's second law over here for block B, the net force acting on block B in the x direction is equal to the mass of block B times its acceleration in the x direction. The only horizontal force acting is that force BA, and that's going to equal the mass of block B, which was given as 5 kilograms, times its acceleration. Now, we know the mass, but unfortunately, we don't know the acceleration of either block. I know that they're going to have the same acceleration, so we actually have to find the acceleration first. So, I'm going to use a trick. Since both blocks are accelerating at the same rate, I'm going to look at the net force acting on the system as a whole. That's going to equal the mass of the system as a whole times that acceleration. So we are talking about forces acting in the x direction because that's the direction of the acceleration, so let's be more specific there. So let's talk about the forces acting in the x direction. We have this force AB that's going back to the left, negative FAB. We have the 100 Newton force going to the right, so it's positive 100. And we have force BA, that's going to the right, so that's also positive. And that's going to equal the total mass of the system, which is 25 times the acceleration. Okay, now here's the trick. FAB is equal to FBA. One of them negative, one of them positive. They're gone. They cancel each other out. Internal forces, these Newton's third law action-reaction pairs, will always cancel out when we consider the net force acting on the system, because they're always equal and they're always in opposite directions. So that leaves us just with 100 newtons of force acting on the system divided by the total mass of the system, and that's the acceleration, 4 meters per second squared. Okay, so 4 meters per second squared, that means that block B is accelerating to the right at 4 meters per second squared. So going back up here, the force of B on A, or A on B, is going to be the mass of block B times its acceleration. That would be 20 newtons. Okay, so if it's 20 newtons here, then it's going to be 20 newtons here. Okay, so it's worth noting, why does block A accelerate to the right? Because it's got a net force acting to the right, 100 newtons to the right, 20 newtons to the left. Why does block B accelerate to the right? It's just got a horizontal force of 20 newtons acting on it to the right. Okay, so those equal and opposite action-reaction pairs will always be equal and opposite. All right, if I pushed with harder than 100 newtons of force, the amount of that equal and opposite force could change. It could rise to 30, 40, 50 newtons, but it will always be equal and opposite. All right, the magnitudes will be the same, pointing in opposite directions. That's that problem done and dusted.